Every second, thousands of tons of cargo and hundreds of commercial aircraft are in motion. As a logistical system grows, the complexity of moving these assets doesn't scale in a straight line. It multiplies exponentially into millions of intersecting variables. At this volume, human intuition completely breaks down. Attempting to manually route assets through a congested network leads to bottlenecks and cascading delays. Solving this requires strict mathematical modeling. Look at the Canadian Pacific Railway. Prior to their integrated operating plan, trains were dispatched only when sufficient freight accumulated. This led to highly unreliable delivery times across thousands of miles of track and overlapping rail yards. By discarding their manual dispatch rules and translating their network into a rigorous optimization algorithm, they reduced transit times, lowered fuel consumption, and documented over $500 million in savings. United Airlines faced a parallel challenge. When weather grounds a single flight, the entire schedule fractures. By deploying an optimization model to reassign aircraft dynamically, they reduced flight delays by 50% and saved an identical $500 million in a single year. These $100 million margins are the direct result of redefining the entire physical infrastructure as a computable mathematical object. The discipline that makes this possible is called network optimization modeling. Before a computer can route a single train or plane, the physical reality of steel, asphalt, and time zones must be stripped away entirely. The network is reduced to its first primitive component, nodes. A node is simply a distinct state. It can represent a physical rail yard, a specific airport, or a distinct point in time. The second component connects them. These are arcs. An arc represents a decision pathway or a physical route between two nodes. In most logistical models, these arcs are directed. An arrow indicates a strict one-way flow, mapping the physical constraints of one-way tracks or the irreversible forward progression of time. This structural translation, collapsing chaotic geographic and temporal reality into a strict framework of circular nodes and directed arcs, is the exact prerequisite required to run any optimization algorithm. Once the network is abstracted, the primary objective is usually to find the absolute shortest path from an origin to a destination. In these models, distance is a flexible metric. While it can mean physical miles, optimization engineers frequently use distance to represent the time elapsed or the dollars spent traversing an arc. This table details a routing algorithm using flight times as distance. To navigate from origin SE to a destination, we lock SE as our initial solved state, evaluate adjacent nodes, iteratively calculate cumulative distances, and permanently lock in the absolute minimum value. This greedy heuristic method marches forward, systematically eliminating inefficient routes and solving the network one node at a time. The process terminates when the destination node, LN, is reached, yielding an optimal flight time of 11.3 across a specific sequence of nodes. For a small, static set of routes, this tabular step-by-step logic works perfectly. But when applied to the simultaneous demands of an enterprise-level operation, sequential iteration becomes a computational bottleneck. Return to the massive operational footprint of the Canadian Pacific Railway. Their integrated operating plan requires blocking.
They have to group thousands of individual rail cars to move together simultaneously across the continent. You cannot calculate a single shortest path in isolation here. Every route is bound by concurrent constraints, hard capacities on the rail lines, the rigid schedules of the train crews, and the physical location of the locomotives. In a network this large, the number of potential path combinations increases exponentially with every added node. Attempting to trace every possible route for thousands of independent cars sequentially creates a combinatorial explosion that outpaces the speed of the tabular method. To solve networks at this scale, we have to abandon step-by-step tracing. The routing problem must be converted into a system of linear algebraic equations, allowing a solver to compute the entire network concurrently. We format the network as a minimum cost flow linear program. These equations represent the exact mathematical structure an enterprise solver relies on. The top line is the objective function. The system is programmed to minimize z, the sum of every arc's cost multiplied by the specific flow assigned to it. To execute this without manually tracing paths, the math relies on the strict principle of conservation of flow. First, we mathematically inject exactly 1 unit of flow into the origin node. Second, we configure the destination node to extract exactly 1 unit of flow. For every intermediate node, the equation dictates that the flow exiting minus the flow entering equals 0. Nothing is lost or created. Finally, flow across any individual arc must be constrained precisely between 0 and 1. By expressing the physical movement of a plane or train as a strictly conserved algebraic integer, the computer no longer traces a map. It solves a giant matrix of equations, testing millions of permutations simultaneously to find the absolute minimum cost. United Airlines applies this exact minimum cost flow framework when managing its fleet. When an aircraft is unexpectedly grounded, United cannot manually guess how to rearrange the remaining planes. Reassignments must happen instantly to prevent cascading cancellations across connecting hubs. In their linear programming model, supply nodes are available aircraft, and demand nodes are required flights. The solver outputs a flow of exact 1 across a specific sequence of arcs. This single optimized path dictates aircraft reassignment through the daily network. This direct application of linear algebra reduced United's flight delays by 50%, preventing compounding disruptions and saving $500 million in delay costs in under 12 months. The results are just as tangible with the Canadian Pacific Railway. The optimization model completely reorganized how physical assets move across the continent. Transit and dwelling times dropped. They balanced crew workloads, consumed less fuel, and maintained operational output while systematically reducing the total number of railcars they needed in circulation. The highest level benefit to the organization is operational agility. Because the entire physical network is mapped as algebraic parameters, CPR can alter the variables to instantly shift resources and respond to real-world disruptions. Translating physical chaos into a matrix of constraints and objective functions creates a measurable competitive advantage in efficiency, resource allocation, and response time. It provides the mathematical precision required to turn operational volatility into a predictable, agile asset.